Păunescu from the Institute of Mathematics of the Romanian Academy. And he will tell us about the permutation stability of amalgamated products over finite groups.
Thank you for the introduction, and I want to thank the organizers for the invitation, and I want to congratulate them for the idea of such a workshop. So it's always a pleasure to be in Cambridge and to give a talk in this perfectly designed room for this activity. So my talk is about permutation stability. I will start with rewriting the definition, and I will also establish some notation for the rest of my talk. So we'll fix a sequence of natural numbers, and I will work with sequences of maps. So phi, it will be just a sequence of maps from a group into symmetric groups on dimension nk. Okay. We saw this type of objects before under different names. So I will call such an object a morphism if each of these maps is a morphism. Or alternatively, you have a morphism from the group G into the Cartesian product of symmetric groups. And related to this, it will be what I will call for this talk the notion of sophic morphism. So again, I'm talking about a collection of maps, now just maps. So such a collection of maps will be called a sophic morphism if you have this condition that the Hamming distance of phi kg, phi kh, and phi k of gh is going to 0 as k increase, and this happens for each two elements of the group. So there are different names, almost homomorphism, or I will call them sophic morphism for this talk. And the third definition that I need, the equivalence. So two sophic morphism or morphism will be called equivalent if the Hamming distance converges to 0. So if they are equal in the Hamming distance. So phi c are equivalent to psi if the Hamming distance between phi k of j and ck of h goes to 0 for each element of the group. And of course, this is just to hide the fact that we actually have a sophic morphism is a morphism from the group G into the ultra power of these groups. I do this because I know that not everybody is familiar with ultra product language, and maybe a talk is very difficult to follow if I use ultra products all the way. But if you are familiar with the language, you know that a sophic morphism is actually a morphism from the group G into ultra product of symmetric groups.
So in the last slide, you have some H.
I have some H, yes. So this should be G, sorry. This should be K. Thanks. Okay, and the definition that we saw today, so G is stable in permutation, or P stable, if any sophic morphism is equivalent to a morphism. If any phi sophic morphism, there exists psi, a morphism, such that phi is equivalent to psi. And I will also write this result to discuss, so joint work with Nara. Abelian groups are stable. Let's say about Z2 is P stable. This is just a fancy way of saying that if you have two permutations that almost commute, then you can find two permutations that exactly commute nearby with respect to the Hamming distance. So I will write a commutation relator like this. And what I want to say about this result is that if you check the proof, and also if you check it on some particular examples, you'll get different type of geometries and combinatorics. You'll see that you'll use your errors, so you are allowed to change a little bit your permutations. You'll use that errors in order to split your permutation into more cycles. So the motto for my talk will be large cycles are a problem for P stability. So in general, you can see here, you can think of this relation. This is why I wrote it like this. As the permutation A acting on B. And if you want this to be equal to B, then you'll see that this action on A will impose a certain cycle decomposition of B. A, it will tell you that, it will tell B, these points should not be in the same cycle, in your cycle decomposition. This is what is happening. And as Gulnara said, we also studied this problem with a stable centralizer. So you need to be able to change both permutations in order to get the stability result. If you ask what happens if you have one permutation, meaning one sequence of permutation fix, can you always find change the second permutation in order to get the commutation? And the answer is no, you cannot do that because your permutation A might have large cycles. So I will state the result for the definition. So if I take P, so now it's just a sequence of permutation, or alternatively you can view it as a morphism from the integers Z. I will say that this has stable centralizer. If for any other element such that they almost commute, so Pk is equivalent to Qp. By this equivalence I mean exactly the same definition, but here I wrote it for morphism. So here I'm just taking two elements and I'm asking them that in the limit the Hamming distance goes to 0, then there exists R, another sequence that is equivalent to Q, such that you have exact commutation now. PQ, PR is equal to RP. So in order to describe which elements of Cartesian product of symmetric groups have this property, it's kind of difficult to write it without ultrafilters, but I will do it. So P has stable centralizer. You can ask for P to have a global bound on the cycle structure. That will be enough, but it's not necessary because P can still have large cycles, but they might occupy a trivial space in the limit. So what you have to say is that any sequence Mk such that Mk over Nk goes to 0, then you have this relation that the sum of the length of the cycles of the first Nk cycles over Nk, this goes to 0. So where Pk has this cycle decomposition, psi k1, psi k2, and however there may be. So take your permutations, take the cycle decomposition, order the cycles in decreasing length. So ck1 should be the cycle of the largest length in the cycle decomposition. And then I'm saying that the sum of largest cycles in pk should occupy a trivial space. So for example, if you take nk to be k squared, and if you take this permutation pk to be a permutation that has a cycle of length k, and then only fixed points, k squared, then in the limit this element p, composed of this sequence of permutations, is actually equivalent to the identity. The Hamming distance between this permutation and the identity goes to 0. But this permutation has a cycle that goes to infinity in length. Okay. So this will have a stable centralizer. Okay. And an example of a permutation that doesn't have stable centralizer, if you just take a cycle of maximum length. Then the only permutations that commute with the cycle of maximum length are powers of that cycle, and you can easily construct permutations composed of very many cycles that almost commute with one cycle. So this is an example where this fact with large cycles appears to be a problem. And another reason for studying this type of problems where, okay, you are asking stability questions, but you want to fix some elements. As Bernard said, we arrived at this type of problems when studied stability of amalgamated products. Okay, so when you try to prove the stability of an amalgamated product, at some point in your proof, you inevitably get this type of thing that you try to correct your Stoffig morphism, you try to correct it to a morphism, but on a subgroup, your permutations are already prescribed from the other side. So I'll mention these two articles that appear at kind of the same time. So the joint work with Nara. I will not write the full result, just an example. So case when our theorem can be applied is this group. So this is a p-stable group. For each p-stable G, an H finite. And some results of this type were obtained also by Gerasimova and Shepin. They have some examples, so you can take the double of the group. So the same thing, G should be p-stable and H finite. So the methods are quite different. In general, we still take a Stoffig morphism of the large group, and you try to correct it to a morphism. We use the p-stability of G in order to correct it on this side, and then whatever we get on H, we don't care. We use that in order to correct also this side to a morphism. So this is where this constraint stability that I'll talk in a moment. Their method is kind of complementary. They look at the whole picture of the whole Stoffig morphism, and they first try to give the morphism on H, and then correct it on both sides at the same time. But you can see that, at least for now, we have this general type of results only when amalgamation is done on a finite subgroup. And this is, again, because, and hopefully I will manage to show why it's difficult to get it otherwise, is because when you have a morphism from a finite group, then you know that you only have small cycles. So now, of course, I want to talk about the general methods to obtain this type of results. And this is another result where the main tool in the proof is amenability. As you saw in the previous lectures, amenability can be used to get results also about Stoffig groups or hyperlinear, and about Hilbert-Schmidt stability or permutation stability. And in my point of view, it's something inherited from the theory of von Neumann algebras. So in the theory of von Neumann algebras, we have a very good understanding of what amenability is, and hyperlinearity and also sophicity inherit this knowledge. So to better exemplify this, just for this part of my talk, I will quickly switch to hyperlinear morphism instead of Stoffig morphism. So just for this part, I will use maps from the group G into unitary matrices. So for now, we have a collection of maps from G to U and K. And the same thing with the hyperlinear morphism. I don't want to write it again. Just replace Hamming distance with Hilbert-Schmidt distance that we saw in the previous talk. And to this object, you can associate a trace or a character. So trace of phi is a function from G to complex numbers. Trace G phi of an element is limit in K of trace of phi K of G. So this is a unitary matrix. It is a matrix. It has a trace. This will be a bounded sequence. You may complain that the limit might not exist for all elements, and you would be right. This is where ultrafilters come in handy. You can pass to ultrafilter, or you can restrict yourself to work only with morphisms for which this limit exists. Okay, there will be no loss in generality if you do that. If you don't like ultrafilters, and I want to introduce this definition that plays an important role in stability results, namely conjugacy. So we'll call to hyperlinear morphism, in this case conjugated, if there exists a collection of matrices, of unitary matrices, such that when you conjugate one of the morphism, you get something equivalent to the other one. So conjugate one with a sequence of unitary matrices to get another hyperlinear morphism, and you want them to be conjugated according to this definition. Replace summing distance with Hilbert-Schmidt. And the classic result, I think it's folklore. It was kind of difficult for us to attribute this result. So we find something in an article by Hadwin and Shen that is contains something like this. So if G is amenable, then two hyperlinear morphisms are conjugated if and only if they have the same trace. Then phi C are conjugated if and only if trace of phi is equal, trace phi is equal to trace of C. So this is another dichotomy where something it happens for amenable groups and is something easy that we can understand, and for non-amenable it's dragons. So for a non-amenable, the space of hyperlinear morphisms that will correspond to a trace, at least to the trivial trace that gets everything to zero except the identity, is non-separable. So in case G is amenable, it's only one point. You have basically only one morphism. If G is non-amenable, it's completely wild space. And this theorem can be used to obtain the Schulman and Hadwin and Schulman criterion for stability of for Hilbert-Schmidt stability of amenable groups. So what happens in the case of Sophic morphism? The reason that I'm saying is that this theorem comes directly from the theory of von Neumann algebras. You can use the von Neumann algebras to prove something like this. So what happens in case that you are working with Sophic morphisms? So collection of maps from the group G to permutation matrices. For a lot of time we had just this result, classic result of Elek and Szabo. That we know that two are conjugated, so G is amenable. Then let's say phi C are, I will say P conjugated. Meaning that now that I have two morphisms, of course I want them to be conjugated by a sequence of permutations, not just unitaries. So RP conjugated if trace phi of an element G is equal to 0 is equal to trace C of G for each element that is different than identity. I kind of write it messed up, I should say. Two morphisms with this property. So I'm not only asking the traces to be equal, I'm also saying that they should be equal to 0 on non-trivial elements, because trace of identity will always be 1. Then you know that they are conjugated by a permutation, by a sequence of permutation. Of course, that you can also define trace for Sophic morphism, because you can see a permutation as a permutation matrix and take its trace, or you define it directly as the ratio of fixed points of that permutation. And in general, this theorem fails. So we have examples, they are not that difficult to construct, where you take two Sophic morphisms, you arrange that they have the same trace, but not equal to 0. You will know that those Sophic morphisms are conjugated by a unitary matrix, by a sequence of unitary matrices, but they are not conjugated by a sequence of permutations. And this, at least me, took a lot of time to understand why. And the reason is that there is an extra invariant. Okay. So here, of course, that if you want conjugacy, you must have equality of traces. That comes from matrices. The fact that you are conjugated with the matrix. So what happens for permutation is this action of the symmetric group that is acting on a set of n elements. And if you take a permutation here, it will have a number of fixed points. And you can conjugate it with another permutation, you'll get the same number of fixed points. Traces have to be equal. But what you can do now is to take two permutations, P and Q here, and to look at the set of fixed points that are at the same time fixed points of P and fixed points of Q. And if you conjugate these two permutations with a matrix, that quantity gets preserved. But if you conjugate them with a unitary, that quantity might be not. So this is where we define this notion of, we called it action trace to have it in the same picture as that. So it's something that you can define for an action. If you take an action, a measure preserving action of a group, you can construct for a finite so this is the collection of finite subset of G. For such a finite subset, you can define this value, the measure of the set of points X that are fixed by all the elements in A. Okay. And for a Sophic morphism, so phi is a Sophic morphism, I'll define similar to the definition of trace. I'll define it action trace to be the limit in K of 1 over nk, the cardinality of the points I that are fixed by all these permutations. Pk j of I is equal to I for each G in A. And at this stage, without the ultraproduct language, it will be difficult to convince you that this is actually the same definition. As Gulnara mentioned, when you have a Sophic morphism, you actually have an action of the group G on the Loeb space. That is an ultraproduct of these spaces. It's the ultraproduct of picture of this action here. And then you can use this definition to construct the action trace. And yeah, having an action trace or an invariant random subgroup is actually the same information. So the definition of invariant random subgroups is a G invariant measure on the set of subgroups of G. And there is this nice result by Habert, Glasner, and Virag that every invariant random subgroup comes from an action. Let lambda be an invariant random subgroup, then there exists a measure preserving action such that lambda is the push forward of the stabilizer map. So stab is just a map from X to the subgroups of G, where to a point X you associate its stabilizer under the action alpha. So it is a sum. And once you use this theorem, so if you take an action, you have an invariant random subgroup, and you have an action trace, and they're linked by this formula, that action trace of a finite set is the measure lambda evaluated on the subgroups of G that contain this finite set. Okay. Sorry. H. Okay. Now, the corresponding theorem to the Haydn-Shen theorem is that two sophic morphisms are p-conjugated if they have the same action trace. So this is basically a theorem in graph theory by Newman and Schauer, but in this context of p-stability and ultra product, it was brought by Becker, Lubowski, and Tom. So phi C sophic morphisms sorry, of course, G amenable. We really need amenability. G amenable to sophic morphisms, then phi and C are p-conjugated. If and only if they have the same action trace. And let me also write what. So I want to state the criterion, the characterization of p-stability for amenable groups. So I will need this definition of residually finite action trace. So an action trace in general is called residually finite if it comes from a morphism, not only sophic morphisms. So if there exists P morphism such that the action trace is the action trace that you associate with this morphism. Okay. And the characterization of stability for amenable groups. G combinable. G is stable if and only if any action trace is reasonably finite. Or in the language that they use, any invariant random subgroup is cosophic. Is the same thing.
Sorry, could you give an example of two things with that are conjugate by a unitary but don't have the same action trace? So, like, well, what can go wrong when you conjugate by a unitary?
So the example is the group it's in dimension, the group is Z2 times Z2 in dimension 6. And you take these permutations 1, 2, 3, 4, 5, and 6. 1, 3, 2, 4, 5, and 6. And if I multiply them, it will be 1, 4. I hope I'm not. Okay. So that will be a morphism from Z2 times Z2 to S6. And the other morphism, it will be the same. 1, 2, 3, 4, 5, and 6 are fixed points. 1, 2, 3, and 4 are fixed points. And 5, 6. And then 1, 2, if you multiply those, 1, 2 will be fixed points. 3, 4, it will be a cycle. And 5, 6, it will be a cycle. So each permutation here has trace 1 over 3, 2 fixed points in dimension 6. But these 3 permutations here have common fixed points, and these have no common fixed points. Okay? Because these matrices here, they don't have common, if you see them as permutation matrices, they don't have common fixed points, but they have 2 common eigenvectors. And the unitary will conjugate 5 and 6 into those 2 common eigenvectors.
Thank you.
Okay. Thank you for the question. Yeah, so what I want to do now is to go to this constraint stability notion and see there what amenability can do. So now I will work with a pair of groups and phi a morphism from the subgroup. So this is morphism, not Sophic morphism. And I will say that G is constraint stable phi constraint if any morphism theta so this is a Sophic morphism that restricted to H is equivalent to phi, there exists psi a morphism such that psi is equivalent to theta, and now psi restricted to H is equal to phi. Okay, so compare this notion with the notion of stability. So for each Sophic morphism, you find a morphism that is equivalent to the first one. So now I'm saying the same thing, just that on the subgroup H, I'm prescribing you the permutation that you use. I'm saying you are obliged to use phi when you try to find your theta that is equivalent to, when you try to find your psi that is equivalent to theta. Okay. So once you understand this notion, then you can see this theorem that Gulnara mentioned. So if G1 is p-stable, let's say G1, G2, two p-stable groups, G2 anyway to be p-stable, H common subgroup such that G2 is phi-constrained stable for any phi morphism on H, then the amalgamated product, G1, G2 amalgamated over H is stable. And the proof is quite direct. So you take a sophic morphism here, you restrict your sophic morphism on G1, you correct that to a morphism on G1, you restrict that morphism on H, and that is your phi that you'll use to correct it here. Okay. I don't think that I need to write it down. Apparently, people understand what I'm saying. So of course, it's not much of a theorem. The difficulty is finding pairs of group H, G2 such that you have this condition. Okay. And what I'm saying is that it is another thing that amenability can provide. So in order to show how examples arise, I will need to tell this notion of constraint stability for action traces. I'll write here and then I will put the table up. So if I have the same thing as in this definition, so a pair of subgroups on the fixed morphism on H, I will say that and an action trace, so finite subset of G to 0, 1, I will say that is phi constrained if the values on subset of H are coming from G. For each finite subset of H, then the action trace of A is the one that phi would provide. You can associate an action trace to phi. And the second thing, an action trace is residually finite. This is phi constrained residually finite. If there exists a morphism from G, so morphism, not just sophic morphism, such that the action trace is the one provided by theta, and theta restricted to H is phi. So the same thing as residually finite. Where did I write? So an action trace is residually finite if there exists a morphism that implements that action trace. Now I'm saying, okay, I want a morphism, but I want this morphism to be this prescribed phi. And the theorem that you can prove is that if you have a pair of groups G amenable and H finite, take your prescribed phi from H morphism. Then G is phi constraint stable. If and only if any phi constraint action trace is phi constraint residually finite. Okay. So you can see so the same criterion of here, just that everything is this constraint. So we need H finite. This is not valid if H is not finite. In the article we wrote that we don't believe. Now I can present also an example where this fails if H is not finite, and it will be because of large cocycles. But before presenting that that example, I want to show some examples to this theorem. They were discussed, but I want to show that these theorems are not just B-theorem mathematics. We can really use them to get concrete examples. So, are there questions? Okay. So, one instance where you can use this this criterion is this result. That if you have an amenable group with countable subgroups, and every almost normal subgroup is profinitely closed, then GSP stable. Actually, if you have only this condition that countable many subgroups and almost normal subgroup is profinitely closed, then you know that any action trace is residually finite. And if additionally you know that the group G is amenable, then you can apply this criterion. Okay, so example, Vaslav Solitar 1n, where you can apply this thing. So AB A minus 1 is equal to e to the power n. So the fact that you have countably many subgroups, so it greatly reduces the number of action traces or invariant random subgroups that you can have, and this other condition will guarantee that the one that remains are residually finite. So how can this result be extended? If we have a pair of groups, the same thing, so H finite, and the same thing as before, G amenable, countable many subgroups, and almost every almost normal subgroup is profinitely closed. And additionally, I will need what we call extension property. I'll write in a moment what this means. Then G is phi constraint stable for any morphism phi. any. So extension property means that just that if you have phi a morphism from H into a symmetric group, so that is just one morphism, this can be extended to H. There exists psi, a morphism of G, such that psi restricted to H is equal to phi. Okay. And one possible example where this proposition can be applied is a finite subgroup on bounce-lax solitaire 1n semi-direct product with H. And this together will give the result that that I mentioned at the beginning, that if you take any p-stable group and you do amalgamation over H with this product or any other pair of groups that satisfy this statement, then you get something p-stable using this theorem. Okay. And now in the remaining time, I want to show an example where if H is infinite, then that that theorem fails.
Sorry, so that doesn't matter in which way H acts on BS1n.
It doesn't matter in which way, doesn't matter the action.
So, but how many finite subgroups does the automorphism group of BS1n have? Like, does it have complicated finite subgroups, or?
But you don't need a finite subgroup here.
Of the automorphism group.
You
I
need
mean, like, in which way can a finite group act on BS1n? Is it very restrictive? Or?
To be honest, I don't know exactly how many. If you know something that can.
Okay.
The two, I guess, it can act if you switch the generator to something that I will do now.
Okay.
Actually. I guess I can erase this. So the example that I want to talk about is integers as a subgroup of Z acted by Z2. So this will be generated by A, and this is generated by A and B with the equation D squared is identity, and B, A, B is A minus 1. And phi is just the largest cycle. So phi k from Z to S and K, phi k of A of E is I plus 1, modulo nk. So the largest cycle. And the statement is that if you have an action trace that is phi constrained, then it is the free action trace. It is the action trace associated to the free action. So then action trace of A is equal to 0 for each A that contains a non-trivial element. So A should be different than the one containing only. If you have only the trivial element, then this of course has to be 1. So this is reasonably finite because you can take theta of B to to be the switch of the permutation. So nk plus 1 minus e, theta b of e is nk plus 1 minus b. Yeah. So just send the point into its opposite. Symmetrization by the middle of the side. And of course theta k of a should be equal to phi. Okay, should be equal to phi k of a. So you can see that theta k defined like this is indeed a morphism, not only a Sophic morphism. It indeed respects these two conditions. So that means that this action trace is reasonably finite. So any action trace is reasonably finite, but this group is not phi constraint is stable. So that's one part of the example. The second thing is that Z is not phi constraint is stable. And the way to do it, you just take symmetrization of two parts. So theta k b of I will be nk over 2 plus 1 minus e on the first half of the interval. So e from 1 to nk over 2. And on the other side, I'm doing another symmetrization. So this will be nk plus 1 minus I for I from nk to plus 1 till nk. So now theta k together with that phi k of a will only be an almost morphism because you'll have some errors here. And if you want to correct this to a morphism, then you'll have to change your phi. You'll have to divide phi into two cycles be given by this permutation. So this is what I'm saying, that when you act on a permutation with some other permutation, then sometimes you are imposing a cycle structure on the permutation that you are acting on. Okay. Like, so yeah, this cannot be corrected to a morphism without changing phi. Okay, I will stop here.
Questions to Liviu? Actually, we have a technical question.
Yeah.
You said that the action trace and the invariant random subgroup are much the same.
Yeah, you can pass canonically from one to another. Yep.
So I wanted to ask if you connect this philosophy of large cycles precisely. So if I'm trying to correct the Sophic morphism where there are no large cycles for any element, can you do this?
First of all, what does it mean that there are no large cycles? There exists a global bound, or
Global bound says the strongest condition you could
yeah, it's the strongest condition. And what you like to obtain?
to find a close homomorphism to such a
Well, that would be equivalent to the fact that the finite groups are p stable, no? If I understand correctly the question. Because having only a bounded, if you have a collection of sequences of permutations, am I missing something?
I think he's right. So the group can be infinite, but you always have a specific Sophic morphism, like always small cycles. Is it always possible to correct it? So you don't correct every Sophic morphism, but just specific ones which
For
are
each element of group, you have only this thing. Isn't there some way to get to a finite, to collapse everything to a finite group? In this case? Or you get to Burnside problem?
no, sir. No, he's not saying that every kind of morphism is like this. He just restricts to certain.
Yeah, I understand. I understand. You want for that specific morphism to correct it to a sophic morphism to correct it to a morphism. I don't know how to say if it's correct or not, but it might be possible. I mean, I would not be surprised if you can do it. I don't know to say.
More questions?
Maybe I will make a comment. I'd like to attract people's attention to this extension property, which is a bit hidden. If you can move it a little bit up. Yeah.
No.
Yeah, just like this. So it's interesting. We would like to extend homomorphisms to symmetric groups only. So it's a kind of I saw this property appearing in computer science and also in three manifolds when they it's not like all, but only to symmetric groups. So it's interesting to have and we need this property, and we have some variants of this property. So it's interesting to understand a little bit better which kind of pairs or G and H we can have in this property. Just a comment.
And in the problem, it's the SNs, the N is the same in both S's, right?
No, for any morphism to any SN.
No, but the extension, are you allowed to increase N or not? That's absolutely key.
That would be a variant.
Yeah.
Right? So, but which is the problem?
It will be flexible extension.
So N, you're allowed to increase N to M.
If you are allowed to increase F.
If you want stability, then you need it like that.
Yeah.
If you want flexible stability, then you are allowed.
Well, it's your problem, so I don't know what you want.
So for this result, the way I wrote it.
So that's stability, but I see. So N is N. It's N. It has to be N in both.
It has to be N, but it will be interesting also if you allow to increase the size, but then you only get...
It's a kind of weakening of retraction property, yeah? Which is a kind of interesting even algebraically.
So the way you prove it there is because it's a retract?
No,
Or
we
no?
have we have examples which are not necessarily retract. This
Yeah,
is just
no, but here, yes.
It's just
just
one
an
example,
easy,
yeah.
just an easy. So it's not equivalent to retract. This is why I think it's interesting.
Is it retract with a bunch of virtual everywhere?
No, I don't.
We also just define an index.
Okay, so we have a tea break and we resume 3:30, and let us thank Liviu again.